rotate, and someone has to be there, me. Play defense.
It's always,
I've been crazy sick, so like insane things, like balls about to go in there.
heck yeah. I've had one mistake. I was
like those double saves, where you hit the ball, but it's still coming in, and try to smash it in, and you hit like that too.
That's, defense is the most important thing.
The rotation.
Yeah.
Behind.
My,
And it's like, there's those dumb luck shots where like, going for it, and like, pinch it.
I've been doing, college and this one's trying to do ballistic saddle.
Pinch it. I think it's our pinch.
How fast is that? Jesus Christ. That goes working. Jesus, that's unsafe. I was playing orange yesterday. I got shot. I got a couple of days.
I've been doing good with the class. I keep my class or good shots.
All right.
I'm good at those shots for some reason.
So we can now make predictions. By the way, Thomas, what the butthead mistake was that the energy was 1/2 of what I wrote down. And I erased it at this point, but it should have been an 8 here, not a 4, which basically cut everything in half.
Okay.
For the aeronautical, he was 4-5.
Yes.
When he wrote it over, he copied 4-5.
Okay. So, I got my proton right here, I got an electron here at n is equal to, let's start out with n is equal to 3. It's not stable, and so the electron drops down to n equals 1. It loses energy. Let's figure out how much energy was lost. I have a formula now that my energy is equal to negative 2.17 times 10 to the negative 18th joules times 1 over n squared. I start out with n is equal to 3, so I'll just write it E3 is negative 2.17 times 10 to the negative 18th joules divided by 9. And it goes down to E equals 1, negative 2.17 times 10 to the negative 18th joules over 1 squared.
Well, E1's just gonna equal 2.17 times 10 to the negative 18.
Good job.
And this one will be, well, that's divided by 9.
Yeah.
So negative 2 point something times 10 to the negative 19.
2.412.
That's what.
412.
All right, so the electron obviously lost energy because there's less energy here than here. So let's figure out the change in energy of the electron. Change in energy of the electron would be final energy minus the initial energy, or negative 2.17 times 10 to the negative 18th minus negative 2. Well, let's put it in the same units there, 0.2412 times 10 to the negative
1.93 times 10 to the negative 18.
1.93?
Yep.
So if the electron lost 1.93 times 10 to the negative 18th joules, where did it go?
Is emitted as light.
Oh.
And so the energy of the emitted light would have to be the amount that was lost, or the opposite of that. 1.93 times 10 to the negative 18th, and that should be equal to h times the frequency. So we can now predict the frequency of the light that's coming out. So the frequency would be 1.93 times 10 to the negative 18th divided by h, which is 6.626 times 10 to the negative 34.
It sounds familiar.
Basically, that times 2 pi.
It sounds like a number that I've heard.
Negative
Yeah.
1.83 times 10 to 16.
Pardon?
Negative 1.83 times 10 to 16. Or did I miss?
Huh?
Never mind, I missed something up.
Oh, for that final?
Yeah.
Uh,
Oh, yeah, I definitely did. miss.
6.626,
I did.
it was indeed the correct number,
Yeah.
negative 34th.
I used the wrong number. I used the H.
No, so you're off by a factor of 2 pi.
Oh, okay. Just multiply that two. Hold on, let me do this.
Yeah. Oh. Was it 2 point something?
Yeah, 2.913.
2.913
Yes.
times 10 to the 15th
Yeah.
units?
Hertz.
Yep. This would be joules divided by joule seconds. The joules would cancel out, and you're left with whatever seconds. This hertz. All right. So that's the frequency of the light that is being emitted. We can now figure out what the wavelength is to see whether it's in the visible spectrum, because typically we have those numbers down, at least I have those numbers down, better than the frequencies. And we'll squeeze it in over here. So I know that frequency times the wavelength is equal to the speed of light, and therefore my wavelength is the speed of light divided by frequency. So roughly 3 times 10 to the 8th meters per second divided by 2.913 times 10 to the 15th hertz.
1.029 is 10 to the negative 7.
So about 103, so approximately 103 nanometers. This is outside the visible spectrum.
That's what I got.
All right. Thank you for confirming. But we do have, let's try another one. Let's go from 3 to 2. So if this goes from 3 to 2, that stays the same. This now is divided by 4. So negative 5.5.04 times 10 to the negative 19. Colton?
I was just curious, this is the photoelectric effect still,
No,
right?
it's not. No, this is the discrete spectrum. This is based upon what Bohr's major assumption to be the quantized angular momentum. He came up with the radiuses that I wrote over there. That the radius of an orbit is equal to the Bohr's number times some positive integer squared. Those are the only possible orbital radii.
Oh, I forgot what we were on, it's all,
And the fact that the energy in those levels is equal to, we've got this negative 2.17 times 10 to the negative 18th joules over n squared. And those are the possible, and those are the energy levels for those particular orbital radii.
I was just wondering, cause cause it sounds like, cause I was just thinking of, this is how solar panels
Oh, yeah,
and photoelectric sensors work. Well, that's what I was thinking, I didn't know for sure, because,
yeah, it's not photoelectric, it's, probably more closely related in terms of everyday life, of how our cells generate energy, I think.
Oh, I got it.
266 nanometers.
What?
Oh, all the way over to.
Oh,
you
I'm
jumped
sorry, I
over
thought that's as far as we go on this.
here. So 200 and,
66, or 67 rounded, sorry.
that's, what, would that be, gamma rays or X-rays?
Oh, no,
alright, so, this is shorter wavelength than visible, which means a higher frequency, which means higher energy. Higher energy would put it into ultraviolet, probably ultraviolet, would be my guess.
Yeah, it's not in the ionizing range. Ionizing radiation is part of the electromagnetic spectrum, isn't it?
Well, any radiation that ionizes, I mean, ionizing radiation is electromagnetic radiation, typically.
Oh,
I guess you could get bombarded by other things that were labeled as radiation. I mean, beta radiation is just basically electrons. Alpha radiation is helium nuclei,
Then gamma radiation.
which is electromagnetic.
That is ultraviolet.
So we still can't see it. However, we can see other things, and so let's pull out some equipment and hopefully not shock ourselves.
Oh, the Tesla one. Jacob's ladder.
It does warn you. Danger, high voltage.
Can't
oh,
touch it.
boy.
Put a hand in there.
I fried one of these on this thing.
Oh. How many volts are,
It's a micro transformer for that.
I don't know.
Don't touch it.
Probably figure it out.
Oh, right now it's not plugged in, and let's make sure it's off before I plug it in.
Start reading labels.
It's plugged in.
5,000 volts? Or is that just?
Does it say 5,000 volts?
Turn it on.
What were you saying?
That was just making a joke.
Does the math check out there? What's 5,000 over 120? How many watts is this thing?
oh,
So-
what's
42
what's
watts.
that?
Some watts.
This is,
The vacuum tube.
yeah, it's not officially a vacuum, because inside it is helium.
Do I?
Oh,
Biggest
okay.
LED you've ever seen.
Oh,
So it's gonna burn a certain
Wait,
blue, I think.
it's
right?
it'll
Let's
glow
find
like,
out.
it'll glow sorta like the sun.
Orange. Oh, yeah.
Alright, so basically, that's what we're seeing right here. It doesn't really help us. Yes, it's basically exciting electrons are collapsing back down, emitting light.
Beautiful.
Kind of is an LED.
Can't
It's
touch it.
mine.
A very archaic form of LED.
Yeah, that's what I
Think-
think.
More like the neon lamps that we see,
Yeah.
even though this isn't.
It's not in.
Not officially neon.
Solid film.
We've had neon in the past. That's mercury,
Ooh, I wonder what color mercury is.
that in theory is water vapor, but
You have, wait, a thing with mercury in it, would
Yeah.
that?
Yes, thermometer.
Oh, it'll glow like a fluorescent light.
It's a mercury gas.
alright, so basically on the back end of this thing, there's a little groove right there and a slit. We pop this thing out.
Oh, interesting.
So as light comes in, it's basically a single slit here. The way that it diffracts will depend upon the wavelength of light coming in, and that light will get reflected onto here. This is in 10 to the negative fifth centimeters, which is not a traditional unit that we like to use here. So in terms of meters, it'd be 10 to the negative seventh meters. So this 5 right here would correspond to 5 nanometers. So light's gonna come in here and then it's gonna reflect onto this.
Okay. Oh, this is cool.
Yeah, this is.
Yeah, that's a good way, so that's a good way of showing how these,
Make sure this is lined up. Do this before I turn it on, because I've learned.
Have you been?
That's one thing I have not done.
You have not been hit by that?
No, yeah, once was enough. But touching
What,
an
120?
outlet, yeah, 120 was enough. All right, so we're gonna turn off the lights, we'll turn this on, and then you look through the viewfinder, and you basically, you're not casting your eyes at this, you would see this, but you're looking over here, and you should see colorful bands over here, some very, you'll see a couple of bands which are, yeah, I can see color there, to ones that are very vivid.
Do we need masks for this, or?
Oh.
I don't know
We
how
don't
big
have
it's
a
gonna be our viewfinder.
Yeah, so just sort of stand back till you take a look. Assuming it's not pitch black. Alright, so who's going first? We just going in this order right here?
yeah, I'll see.
Alright.
I'll let, well, let's let Thomas go.
Oh, that is cool. There's like all different colors.
What's the most dominant color?
Yellow.
And what's the number?
I can't see a number.
Okay.
This is good.
So yeah, all I can see is the colored band. The number is not visible.
Can I, take a look? I'll try to.
Yeah.
Let's see what this is like.
Cool, oh, I can see what you mean by that. Yeah, I'm
What?
not able to see the color. Oh,
Can you see the number now?
yeah, it's,
Do I need to shine
very
it?
close
I can
to
shine the
the,
light.
it looks like it's almost touching the 6.
Let's, because you want some light coming through, but not too much light, so I don't know if that's,
Wait, hold it off at an angle.
yeah. Could you still see the yellow bar and the numbers?
Oh, yes, I can see that. It's very close to the 6, like, yeah, it's very close to the 6.
On the, which
Uh,
side of the 6 is it?
Oh, it's on the, left side, my bad. It's between,
So,
between 5 to the 9,
somewhere around between 5.9 and 6?
yes, yeah, that's what I meant to say, my bad. That's pretty cool, though.
So about 590 to 600 nanometers.
Yeah.
I can hold it for you.
That was really funny.
Yeah, blue's like on 4.5, green's on 5, yellow's on 6, and red is on 6.8.
So there was red, and blue, green,
In yellow.
yellow.
Yep. That's what I see.
And they did something like, and when they were, I forget who discovered helium, but they did did they do something similar to this to,
Oh, that's really cool.
to figure out, that it was another element?
It's really neat.
Oh, when they discovered helium?
Yeah.
They're very like.
I forget, I don't know historically how they came upon those conclusions. I mean, some things will burn, some things will not, so that's the quick test right there.
Oh yeah. Okay, that makes it a lot easier.
All right. And all of you've gone?
Yes.
Okay.
Or here.
Yeah.
Yeah, definitely those 4 bands are indeed
The optimum. All right.
You said that there was one with water vapor?
Yeah, the tube says water vapor on it. There's been some mixing and matching. I don't think it's actually water vapor.
I wonder what the mercury one would look like.
Let's do it.
Yeah, I was kind of thinking, we could see what the other, I was thinking why not to check the other vapors, but that's up.
And it won't burn you, but just if you touch it quickly, but you can feel it that. That's been giving off energy
It's
right
up,
there.
Yeah, heat.
Love this little watching the birds. Just
So, how do I put this thing on?
All right, so the metal basically gets goes in the flames.
Okay, like this?
Yep, and then
Okay.
like that, and then you can adjust it if you need to, but it's already set from last time.
This is your job, just make it as hard as you can.
And,
Or no, sorry, electric.
Yeah, it's lit.
Do you need some, do you need light to see the?
Oh.
I can see, what I see the most of is green. If you could, move the, focus the light up a bit more, so it's away from, a little bit away.
I wanted to go there so I could see the whole.
Okay. A little bit more, a little more,
More light or less light?
less, oh, sorry, I need less.
It's not like less.
I very faintly see green on 5.5. And I barely see blue, which is at I think 4.3.
I think green. It just sounds like a green color.
Sure, it's blue, not violet.
Or
Here, Aaron, do you want the light?
or it could have been, maybe it was
Because I
violet.
can see the numbers.
There you can.
It's definitely is violet.
Oh, my bad.
Those are cool looking.
Oh, yeah, it is kinda hard to see the numbers, so it's still. Oh, there we go, that's better. Oh, yeah, so violet's at 4.3,
Or white skin is
green's
bright
at
enough
5.5,
Guys enough to light it.
and yellow is at 5.8.
How did
White's
you
actually
see
light.
the,
And it's light.
oh,
Yeah. it's yellow.
Oh yeah, you actually can see.
I think part of the
Violet's
problem
way
with the
over to the
light's
right.
coming in from the window.
Oh,
so
it's-
that gets blocked.
Oh, yeah, the house in front.
When you said, wait, I can't see him, it's because Thomas's head was right here.
Yeah.
Alright. So that's, the other one was nitrogen?
helium.
Helium.
Yeah, we did, helium